Hello and welcome to the presentation on Chapter 7 of the International Levee Handbook. We have two presenters, myself, Shaun Wershing, Associate Geotechnical Engineer at CH2M Hill in the UK, and Andy Gaines, Regional Technical Specialist in Hydraulics, US Army Corps of Engineers in the US. In this short presentation, we will try to give you a flavour of the content of the chapter by way of introduction to some of its aspects. The chapter is divided into 9 principal subsections. Section 7.1 is a general overview of the characterization process. Sections 7.2 to 7.5 deal with the characterization of the hydraulic boundary conditions at the toe of the levee and how these are modified and interact with the levee is covered in Chapter 8. Section 7.6 is a short section considering the human interaction on levees, and sections 7.7 to 7.9 consider the characterization of the ground with the emphasis on site investigation. Andy will be dealing with sections 7.2 to 7.5 covering the hydraulics, and I will cover the rest. This slide shows the main content of Chapter 7 and how it interacts with the rest of the ILH. It's a toolbox chapter supporting Chapters 4, 5, 8, 9 and 10. And is not intended to be read from beginning to end, but it's designed to be dipped into to answer the question, how do I? The chapter can more broadly be divided into 2 principal themes. Actions on levees, that's hydraulic actions. These can be considered to be what nature throws at the levee, and human actions. These are things that we do that load or cause change to the levee. The assessment of the physical characteristics of the levee and environs. These embrace geotechnics, which is the structure and geotechnical properties of the ground and levee that are required for the design or assessment of levee performance, and the dynamics of the bed or channel over which or within which the water flows, and the impact of these and the resulting change these cause to the hydraulic actions. This flowchart presents an overview of the whole chapter, illustrating how the subsections are related and how the outcomes of the site characterization feed into other chapters. It starts with the overarching principles and then splits into parallel activities to assess loads or actions on levees in ground conditions. Despite these activities being shown as discrete parallel actions, we strongly advise that there should be continuous interaction between the disciplines. Principles of site characterization. Needs for. Well, if we don't characterize the site, then there are no criteria against which the performance of the levee can be assessed or the design undertaken. Characterization of the hydraulics encompasses the collection of information about the movement of surface water with the aim of developing models that represent physical processes. Characterization of the geophysics involves defining the spatial distribution and properties of the soil forming the levee and the foundations, and assessing existing groundwater regime. It may also include unexploded ordnance, contamination, archaeology, but consideration of these is beyond the scope of the ILH, and specialist advice should be sought. Phased approach. Characterization is best undertaken in several phases, each phase leading to the collection of more data and a better appreciation of the site. It allows subsequent phases to be designed to target known issues. Test study. This is the usual starting point of the characterization process. Guidance is offered on undertaking the test study, on the nature of the information and on the nature of the information that could be consulted. During the test study, a walkover should be undertaken to ground truth the information as much as possible. Guidance is provided on the kind of things to look for during the walkover. Implementing the investigations. This needs to ensure that all key data is collected correctly in a safe manner and is reported. Generally, there are two parties directly involved with the gathering of information: field operations lead and the investigation designer. Some discussion of their roles is presented. Reporting. Consideration is given to the forms of reporting for the various data gathering investigations: hydraulics, morphological, geotechnical. The more demanding of these relates to the geotechnical data, and a typical checklist is presented along with possible approaches for visualizing the data to aid in the understanding and interpretation of ground conditions. The importance of metadata, data about data, is considered along with preservation of the data. An investigation may comprise three phases: reconnaissance, feasibility, and detailed. Within this framework, we consider the activities relating to hydraulic and geotechnical data. The general principles are: with reconnaissance is an initial assessment using existing data for rudimentary modeling and preliminary assessment of preliminary ground conditions. In the feasibility stage, we may develop a better understanding, particularly within the hydraulic data and modeling, and there may be limited geotechnical investigations to support the assessment. At the detailed phase, the concentration there, or the focus, is on the geotechnical assessment and updating or refining the hydraulic data. From a geotechnical perspective, the figure shows how LiDAR can be used during the reconnaissance stage to identify ground features, such as silted up river systems that may or may not be visible on the ground or from aerial photographs. As an example, these tables show how the information could be collected during each of the stages of a phased investigation for hydraulic and geotechnical assessment. The trend is for the hydraulics to be concentrated within the feasibility phase and the geotechnics to be concentrated within the detailed phase, but input from these elements is required during all phases, as we have previously seen. I'll now hand over to Andy, who will take you through sections 7.2 to 7.5 of the chapter.
Thank you, Shaun. As Shaun pointed out in section 7.1, there are two areas that must be characterized. Those are loads and actions on levees, and then the ground conditions. Hydraulics and related topics in the handbook focus on characterizing loads and actions. Geotechnics focus on characterization of ground conditions. River, coast, and estuary settings are addressed. To gain an understanding of how water acts within a system, 4 areas must be considered. These 4 areas are characterizing flow and boundary conditions, identifying other factors that affect water levels, analyzing water levels to include modeling and uncertainty, and assessing system morphology and its effects. These must be addressed in light of each of the 3 areas of river, coast, or estuary settings. There's a flowchart, figure 7.8 in the ILH, that gives the sections to use in going through this process. Section 7.2 identifies interactions and influences between various factors and processes that act upon levees. For example, the water level acting upon a levee is influenced by catchment hydrology in terms of quantity and rate of water, by channel and floodplain hydrodynamics, in other words, water level and timing, and by stream morphology, systematic changes and local influences. There is also an influence or interaction between each of these, one upon the other, that must be considered when locating the levee within the floodplain. Section 7.2, next slide. Section 7.2 also identifies other natural processes that act on the levee. These are shown here with some of the actions that occur. Next slide. A list of principal action categories are given with the corresponding action and suggestions to consider relative to levee projects. For example, in this table, rainfall may cause surface scour on the levee embankment, but providing adequate surface protection can mitigate this effect. Next slide. Section 7.3 presents morphological and hydraulic actions for levees in a river environment. Of primary concern is gaining an understanding of river characteristics and determining hydraulic actions. To accomplish this, data are needed to evaluate discharge, water levels, channel geometry, channel roughness, and a number of other parameters. Key data requirements with methods to measure or calculate their values are described. Because measured data are often limited in scope and time, there is always uncertainty when estimating hydraulic loads. As illustrated on this slide, there's a range of estimated water surface profiles that exist for a stream, depending on whether the analysis is based on minimum, mean, or maximum assumed conditions. The possible variations represent uncertainty in data and modeling approach. It is possible to develop a probability distribution function to describe uncertainty for a given location. That is the red line shown on the graph. This function, combined with risk-based analysis, can be used to determine appropriate hydraulic loads needed for the design of levee projects. Next slide. Section 7.3 identifies the critical need to identify the channel stream type for a stream. This is a critical step because the various stream types have different potential impacts to levee integrity, some being severe. The leftmost column identifies a variety of channel types in this table. The third column, go back to the previous slide. The third column indicates some of the particular stability problems that would affect levees, and then the rightmost column identifies some potential impacts to the levee integrity. Next slide. Rivers are dynamic systems that are a product of their environment. They respond to a number of variables and change over time, sometimes very rapidly. The lower left figure shows gauge height data for a river over an extended period of time. Note that gauge height varies from an extreme low of just below 10 meters to a maximum of over 45 meters during the data period. The lower right figure shows gauge height for a selected discharge values over time. Increases or decreases in gauge height for a given discharge value indicates a change within the system and its influence on the system response. Consider the line representing discharge equal 50,000 cubic meters, which is the top line. This line shows an increase in gauge height midway through the time period. Such an increase indicates a system change that caused the water level to be higher for this discharge. This could be a result of lower stream capacity due to sedimentation or increased roughness. It could also be a result of levee construction downstream of the observation point. It would be necessary to expand the investigation to characterize the source of such a change. Next slide. As detailed in section 7.3, levees may change hydraulic conditions, thereby altering the dynamic equilibrium of a system. It is essential to establish present as well as expected future behavior when setting levee locations and defining goal use for design. Figures A and B here illustrate how levees may influence flood hydrographs. Such changes may radically alter stream response if morphologic thresholds are crossed. A levee should provide its desired function for current and expected loadings. A levee project should also include provisions to maintain its resiliency against possible actions that may result from natural system adjustments. Next slide. Section 7.4 describes morphological and hydraulic actions for levees in coastal settings. Coastal areas are highly complex, as shown in the diagram here. There are many interactions indicated in this flowchart, and it's easy to see in the figure to the right that there are many dynamics. characteristics. Next slide. Next slide, please. The complexity results from cyclical actions over both short and long time frames. Key data needed to assess coastal hydraulic loadings are described in the section. Methods for analyzing the data to determine loadings are introduced, with references given for more detailed explanations. As was the case for a riverine environment, there is uncertainty in both data and analysis results for coastal areas. Next slide. Hydraulic loads that act on coastal levees vary geographically and over various time horizons. The loads comprise a variety of combination of water levels, currents, and wave actions. Shore morphology may change significantly over time, as shown in the slide. It is necessary to know extreme water levels, waves, and currents combined with how the coast will respond morphologically to these loadings. Methods are presented that allow estimation of water levels needed to assess or design coastal levees. Section 7.5 introduces hydraulic actions for levees within an estuarine environment. In this setting, the characteristics of the estuary influence hydraulic loads that act upon levees. For instance, the shape of an estuary may amplify or dampen wave heights. Morphological response and hydraulic actions in an estuary originate from both sea and river sources. Coastal and river analysis techniques are combined to determine the required loads. This is a complex analysis that requires use of a joint probability technique. Tables are presented in section 7.5 that assist in the characterization and analysis of estuaries. Table 737 shown here gives a classification system used to aid in understanding an estuary in which a levee is to be placed. This particular system intends to give a contextual framework for considering how the estuary has developed over time and how that may influence placement and/or performance of a levee. The next table, shown here, is a sample from the ILH and gives a list of questions to use in characterizing estuary morphology. Thank you for your interest in the International Levee Handbook. The remainder of the presentation will be made by Shaun.
Thank you, Andy, for that. We now move on to 7.6, human interactions on levees. These are loads relating to activities such as those listed above. And we have made particular emphasis on the construction, maintenance, and operational loads or actions. For each of these, the nature of the load is considered, but not necessarily quantified, together with suggested loading assumptions and restrictions. Ground investigation for levees. The flowchart shows the areas covered by this section and their interactions both within the chapter and with other chapters. These include planning and conducting a GI, GI relative to failure and deterioration modes, GIs for different scenarios, such as condition assessment, improvement of existing levees, or new designing or building new levees. GI validation through pre-construction trials, and GI through observation on site during construction. Overview of planning and conducting a GI. This presents a discussion on the development of a scope or designing an investigation, and outlines typical interactions that may be required with stakeholders, for example, levee owner, operator, investigation designer, and investigation contractor. Part of the process of developing an appropriately scoped or designed investigation is to have a good understanding of the potential failure and deterioration modes that could impact on the levee, given the understanding of ground conditions based on the depth study and any earlier phases of investigation. Two tables are included within the handbook which summarize the potential failure and deterioration modes. They outline these processes, the forms of investigation that may be needed, and if required, methods of monitoring. Consideration is then given to the discussion of investigations for different levee scenarios. As we've said, these include condition assessment, which is covered in more detail in Chapter 5, improvement works on existing levees and new levees. It also considers the investigation of structures associated with levees and the assessment of borrow materials. GI should not finish on completion of the intrusive investigation. In special circumstances, it may be extended to pre-construction trials and should include visual observations on site during construction, where long sections of new levee are to be constructed or existing levees substantially raised over soft ground. The cost and construction risk can be high. The use of instrumented pre-construction trials can be used to reduce these risks through loading the ground to failure and using back analysis techniques to evaluate soil strengths, or, if not loaded to failure, determining in-situ field consolidation parameters. Existing levees may have an unknown history, and some of the factors to be considered when undertaking investigations in existing levees as a result of past activities could include, well, as a result of construction, we may have some kind of heterogeneous internal structure, or it may even include structures within the in the levee. When we're doing improvement works, side slopes and crests may be formed from different materials, could include dredgings, and it could be relic repair works within the levee to mitigate things such as seepage or breach repairs, which could include aprons, sheet piles, or even deep soil mixing. GI through visual inspection during construction. During construction, activities such as topsoil strip, excavations for drains, soak dikes, borrow areas, or other excavations provide fresh mass exposures of the ground that can give clues as to where ground conditions may be consistent, or more importantly, different from those assessed by the GI. Some examples of observations, possible causes, and potential impacts these may have on the levee's performance are summarized in this table, which is included in the handbook. Section 7.8 looks at the derivation of geotechnical parameters and focuses on those that are most relevant to levees. The flowchart shows the areas covered by this section and their interaction with the chapter and other chapters. It provides an introduction to the different approaches to assessing parameters, along with discussion and guidance on soil classification, determining parameters, and characteristic values. Some of these points are expanded on in the following slides. While soil classification is not considered in these slides, it is worth stating that one of the main takeaway conclusions of the section dealing with soil classification was that there are differences in the various systems used around the world and historically within one country. Therefore, when dealing with third-party or old data, it is important to be clear what system has been used. Definition of geotechnical parameters, as we said, is limited to those most appropriate to levees. These are considered to be the index properties, compaction, shear strength, drained and undrained, compressibility, permeability, and erodibility. For each of these, there is some discussion on the geotechnical properties. To aid in the assessment of the parameters, the following approach has been adopted. Typical values. In the absence of geotechnical data, other than an indication of the general nature of the ground, such as may be derived from geological maps or old borehole records, the section presents a range of typical values of parameters for various soils. Empirical correlations. Where index properties are available, empirical correlations with other engineering properties can be used to derive parameters. A range of published correlations are included in this section. laboratory and in situ testing. Consideration is given to the range of tests that can be used to measure a particular soil property. The application and limitations of each method is presented. Geophysics. The next section in the chapter presents information on investigation using geophysical techniques. For completeness of the parameters section, there is a general table indicating the primary geotechnical parameters that can be assessed using geophysics, along with other related properties. These include properties such as porosity, permeability, shear modulus, and clay content. Having obtained and collected the data on each parameter, a characteristic value needs to be determined to be carried forward to geotechnical analysis. This is covered further in the next slide. Characteristic values. To quote from Bond and Harris in their book on decoding Eurocode, the selection of characteristic values of relevant ground parameters is probably the single most important task that a geotechnical engineer undertakes during design. Although partial factors or other methods of incorporating safety into the design provide a degree of reliability, they cannot compensate for gross errors of judgment in the interpretation of the operational condition of the ground. In selecting characteristic values, some issues that need to be considered include, as we have listed there, codes used, degree of conservatism, going down to data quality and quantity. The figure on the right shows the classic illustration of the forms of sharing that are going to occur under a levee, relating the method of testing to the limit state. Discussion is included on the selection and validation is included in the section on the validation and treatment of data outliers and the need to consider the spatial distribution of the data to avoid overlooking localized areas of adverse ground that could impact on the performance of the levee. In the context of Eurocode, Bond and Harris provided definition of the characteristic value in relation to soil, which acknowledges the large volume of soil that can be affected by the potential failure surface. It considers that the characteristic value should have a 95% probability of being exceeded by the spatially averaged mean, where the lower characteristic value is being assessed. Section 7.9 deals with site investigation. This section covers the processes by which data can be gathered. The flowchart for this section shows that it covers surface information on the left through survey, terrain, bathymetry, hydraulic gauging methods, and subsurface information through the geophysics, intrusive investigation, and instrumentation. The section provides details of a number of methods under each category heading covered by surface information and hydraulic gauging. They typically include information on the principles of the method, its application, advantages and limitations. Some of the geotechnical elements are expanded on in the following slides. Geophysics. Geophysics may not routinely be used as an investigation tool in some countries. However, if expert guidance is sought early on and maintained during the period of investigation and interpretation, then it can add value to the intrusive investigations and understanding of the site. Geophysics covers a wide spectrum of techniques: airborne, onshore surface, borehole, and water-based. It is important to understand the capabilities of the different geophysical methods so that they can be used to their full advantage. To aid the reader, the section includes a discussion on each of the broad techniques. Within each, there are a variety of methods available, and tables are included detailing the methods, deliverables, suggested phase of the project when they are most applicable, considerations, limitations, and daily production rates. Where geophysics is used within a phased investigation, it can most beneficially be done during the early phases before the detailed intrusive investigation, where it can provide a fast site screening tool during feasibility and help target intrusive investigations to maximize the information obtained and to infer ground conditions between points of intrusive investigation. It can also be used to aid in the condition assessment of existing levees. In terms of condition assessment, the section includes a matrix indicating the appropriateness of the various geophysical methods covered in the section and their usefulness in identifying the different features or defects that could be present in an existing levee. Further information on condition assessment can be found in Chapter 5 of the ILH. Intrusive investigations. This subsection aims to provide an overview on the distribution, depth, and methods of undertaking intrusive investigation. In terms of the latter, the section includes tables summarizing intrusive investigation methods, their applications and limitations. Given the locations where levees are typically sited, the ground conditions can include a combination of soft clays, silts, peats, highly permeable sands and gravels. Not all intrusive techniques are applicable to all soils. This is illustrated in a later slide. Intrusive investigations should be seen as part of a phased investigation, broadly starting with the depth study, moving on to non-intrusive geophysics, and then intrusive. The main intrusive investigation phase may be divided into subphases. For example, intrusive investigation may commence with a series of frequent or closely spaced, fast and relatively cheap CPT soundings. These can then be reviewed as the investigation progresses, allowing the supervisor to schedule slower, more expensive and possibly fewer boreholes and in-situ tests that start at a slightly later date in the GI program, adjacent to targeted CPTs to maximize the information obtained, investigate ground anomalies, and develop site-specific parameter correlations of soil properties with the results of the CPT soundings. Levees are linear structures. Some country codes and standards offer guidance on the spacing and depth of intrusive investigations, and these are summarized within tables included within this section. Typically, they all provide relatively similar guidance on spacing in the range between 20 and 300 meters. Fundamentally, the spatial distribution and depth of the investigations have to be sufficient to characterize both the existing levee and the foundations. However, spacing should not be driven by the concept of a fixed spacing, but balanced with targeted locations based on ground features identified in the information available at the time, with depth study, non-intrusive and earlier intrusive investigations. Because of their linear nature, intrusive investigations are often undertaken only along the line of the levee, but soils will also vary laterally across the levee. An investigation should be undertaken offline, as illustrated in the figure. An example of the appropriateness of intrusive investigation methods to ground conditions. As an example of the appropriateness of intrusive investigations to ground conditions, this figure shows a matrix of the intrusive investigations methods covered by this section and an indication of the ground conditions to which they are best suited. When undertaking intrusive investigations, there is, as with all activities, a need to consider access and health and safety. As a levee is often located on soft and on soils that have a high permeability or low strength, access can be difficult. Where such conditions are encountered, discussion should be held with the GI contractor to determine the best approach. Illustrated below are just two examples of special equipment designed to operate in areas of difficult access. These are the modular CPT, or cable percussive rig, the modular cable percussive rig, and a CPT on a long reach excavator. Other specialist equipment is discussed for operating on slopes, over very soft ground, or where there is a restricted width access. Some special considerations that may encompass health and safety issues are also discussed in these sections, and they include working close to water, stable ground contamination, UXO, unexploded ordnance, flora and fauna, and biohazards. While not covered in this presentation, sampling techniques are presented and discussed in a similar format to the intrusive investigations. Specifically, consideration is given to sampling techniques, the quality required to assess particular soil properties, sample size and frequency, and sample handling and transportation. The final section of the chapter deals with instrumentation. The benefits instrumentation can bring include a better understanding of the condition of the levee and the foundation soil, how the levee and foundation soils interact both with and without the hydraulic loading, provide construction control in terms of settlement and the avoidance of the onset of slope failure or instability, validation of design assumptions and ground characteristics through pre-construction trials. The section primarily considers instrumentation which is capable of monitoring displacements and pore water pressures, although total stress, seepage, discharge, soil, groundwater temperature may also be monitored. The section includes discussion on the factors to be considered in the selection, installation, and monitoring of instrumentation. These include the nature and magnitude of the variable to be measured, the need to have some redundancy in the system, and then various records to be kept and maintained, and presentation of the data. There is also a commentary on backfilling of instrumentation installed within boreholes. Some authors advocate using fully grouted piezometers as opposed to installing them in a sand cell. We will leave the reader to decide whether this approach meets their specific needs. A number of examples of grout mixes are presented that have been used in conjunction with instrumentation, but you should note the caution box below. There may be a need to use grout mixes with a much lower cement bentonite ratio. Grout mix trials should be undertaken to ensure its strength is compatible with the surrounding soil and the type of instrumentation to be installed. Lastly, consideration is given to new and evolving techniques. This includes data gathering, transmission, and management techniques. Newer forms of instrumentation considered include discrete monitoring networks or micro-electromechanical instrumentation. These are made up of strings of multi-sensors installed in one borehole. Each multi-sensor can measure temperature, pore water pressure, rotation, and therefore lateral displacements. And the other form is a distributed monitoring system with fiber optics. These work on the basis of changes in the light within the fiber that occur as a result of strain, indicative of movement, temperature, indicative of seepage, humidity, and pressure. The changes can be identified to a location along the fiber to within about a meter. The figure illustrates a potentially distributed monitoring system within the levee.